Section 4 is on word problems, and it's a friendly section in some sense, in that all the word problems will be solved essentially exactly the same way. Each word problem has a short sentence that describes a function that's going to have the graph of a parabola. I'm going to graph the parabola, interpret what the x's and y's mean, and use that interpretation to answer the questions. Problem 2 talks about an object being thrown straight up into the air. It kind of does something like this. You throw something up and it kind of goes up and it comes back down. It follows a parabolic path. And the path that this object that's being thrown in problem 2 in section 5.4, it says the height, h, in feet after t seconds is given by the formula negative 10t squared plus 80t, and then when I fonted this up, the plus 12 got lost. So it gives a formula, and it says the h stands for the height of the object. I guess apparently this should be when a ball is thrown straight up, because of, as I read this, it says when an object, and then it says the height of the ball. So when a ball is thrown straight up, its height, h, in feet, so this is the height in feet on the left-hand side, after t seconds, so the t is the time in seconds, is given by this formula. I'm going to go ahead and sketch a graph of this, and the numbers to the right of the equal sign work like x's, so this is going to be the time in seconds, and the number to the left of the equal sign work like the y's. It's going to be the height in feet. To graph this, because there's two letters, a first and a second power term to the left of to the right of the equal sign, I need the negative b over 2a formula that we learned at the end of section 5.3. And in this problem, the a is negative 10, the b is 80. So when I go to do my table, the number for the middle of my x column was going to be negative b, which is going to be negative 80, over 2 times negative 10. That's going to be negative 80 over negative 20, which is 4. I'm going to get lazy in this section and just do 3 numbers in my table because I don't need that much accuracy. All the work is really going to be focused on the vertex and not the points that aren't the vertex. So these are going to be my x's, which I'm going to write these as t's because it's the x's are time in seconds. And my y's I'm going to write as h. So each one of these numbers represents seconds, 3 seconds, 4 seconds, 5 seconds. And the numbers I get put next to them is going to be how high the ball is, or whatever the object is, in feet. So lazy table, mode 7, and then negative by the fraction 10. I can't do t's, so alpha x squared plus 80 alpha x plus 12. Start at 3, end at 5, step 1. Start at 3 seconds, end at 5 seconds, step 1 second. And the first point is the point at 3 seconds. The ball or the object is at 162 feet. And then at 4 seconds, it's at 172 feet. At 5 seconds, it's back down at 162 feet. So on my y-axis, I have to get really aggressive with my incrementing. This is a parabola that opens upside down. The vertex is a maximum point, hence the word maximums here. And on my y-axis, let me just go by 50. So I'm going to go 50, 100, 150, and 200, and just kind of crudely estimate these. So 3, 162, 4, 172, 5, 162. This point right here, this 4, 172 is the big deal. So the ball does something like this. I don't know how well this is graphed, but it doesn't matter. Each one of the points on the graph is a time and a height. And you can see that the maximum height, this is as high as it goes. This is the maximum height. I can just follow the path. That's clearly the highest point. So that's, and the y's are the heights. And now I'm ready to answer the question because the vertex is going to have what I need. The question is, what is its maximum height? Its maximum height in part B is 172 feet. If I made more numbers in the y column, because the vertex is a maximum point, that 172 is going to be the biggest y. I don't have to worry about having a y bigger than 172. So that's the maximum height. And when does it occur? It occurs at when t equals to 4, which is 4 seconds. To answer my question, when does the object reach its maximum height? At 4 seconds. What is the maximum height for part B? 172 feet. That's all there's to it. Your question 1 should work exactly the same. I give you a comparable formula. You're going to make a table, sketch a graph. If you do enough of these, you don't really even need to sketch the graph. You can figure out the answer without seeing a picture, but I like doing these with a picture. 3 looks grungy. 4 is maybe equally grungy. Let's do 3 together. So this is a similar style of problem. 3 talks about an object being launched from a platform, and it gives a formula in function notation this time, but it still has typos. It gives the equation h of t gives the object's height t seconds after the launch, where the height is in meters. I don't know what this S was floating around here. I don't know how that got by me. But anyways, this formula that's given in function notation, the H stands for the height of this object that's being launched from a platform. The T stands for time in seconds, and the height here is in meters. So the height of this object is given by the formula negative 4.9 t squared plus 19.6 t plus 58.8. I'm going to sketch a graph of the flight of this object in problem 3. The x's, again, represent the time in seconds because the x's are in the position of the t's, and the t's are talking about times in seconds, and the y's are the height in meters as opposed to in feet. So I'm going to make my table again and sketch a graph. So I'm not doing number 4, I'm doing number 3. And because there's both a squared and a first power term, I need to use the formula for the middle of my x column. The number for the middle of my x column, I'm going to use negative b over 2a. The a is negative 4.9. The b is 19.6. So I'm going to get negative b, which is negative 19.6, over 2a, which is 2 times negative 4.9. Don't want to do that without a calculator, so mode in 2 or mode in 1, it doesn't matter. Fraction, negative 19.6 divided by 2 times negative 4.9. That gives me 2 for the middle of my x column. So when I go to do my table, I'm going to do 2 seconds, 1 second, and 3 seconds. So this is time in seconds. And the y's I'm going to get are going to be the heights in meters. Let me get my table on my calculator. I don't want to do these by hand. So mode 7, negative 4.9 alpha x squared, can't do t's on my calculator, plus 19.6 alpha x plus 58.8. Start at 1, end at 3. Step 1 always for me. It says at 1 second, the object's height is going to be 73.5 meters. At 2 seconds, the object's height is going to be 78.4 meters. And at 3 seconds, the height's going to be 73.5 meters. Again, the vertex is going to be a maximum point. And so the y value of the vertex is bigger than all the other y values. So the best I can, really, really crudely graphing these, I'm going to go by 25 is on my y-axis. I don't really need a graph, but I do it anyways. So 1, 73, 2, 78.4. The 2 stands for 2 seconds. The 78.4 stands for the height at 78.4 meters. And this object follows a path that looks something like that. And I can see that the vertex is a maximum point, which means the y-coordinate of the vertex is the absolute biggest y value. Since the y value is the height in meters, it's the absolute height, maximum height. So to answer the questions, when does it reach its maximum height and what is its maximum height, get extracted from the vertex again. The when does it reach its maximum height is the 2, the x-coordinate of the vertex. And for part A, that 2, the x-coordinate of the vertex is the time in seconds. And for part B, what is its maximum height? That's the y-coordinate of the vertex. And for part B, it's 78.4 meters. This style of word problem comes up again and again and again. It comes up in college algebra and comes up in calculus. You just learn more sophisticated ways to solve the problems the higher you get in math. So 5 and 7 are a similar problem. 5 talks about a soccer ball being kicked. It's going to follow a path like this again. And it says, when does it reach its maximum height? What is its maximum height? For 5, you're just going to sketch a graph. You're going to find the vertex. And the x-coordinate of the vertex represents the time in seconds. The y-coordinate of the vertex is going to be height in feet. It's height in feet. So this equation, h of t, gives the height of a soccer ball that's being kicked after t seconds. The right-hand side, the time is in seconds. What you get out is height in feet. So when you go to make a table, the left-hand side is going to be the time in seconds. It's going to help you answer the question, when does it reach its maximum height? The y-coordinates are going to give me the height in feet. I'll skip 6 because it's just like 1, 2, 3, 4, and 5. Exactly the same strategy. And we can take a look at 7 and 8. And maybe we'll do 7 together because it's a little bit strange. I'll do 8, and maybe we'll just even make this a one-part video. So both of our 7s and 8s are kind of the same problem. They talk about the depth of water in a reservoir, and apparently like reservoirs during the rainy season, maybe they fill up and then maybe the water gets used throughout the year and it goes down maybe in the summer. That's probably my theory behind this. And this problem number 8, it says the depth of, or the height in feet of water of the water level of a reservoir over a 1-year period is modeled by the function h of t equals t minus 7 squared. In this case, t isn't time in seconds. T equal to 1 represents January, t equal to 2 represents February, t equal to 3 represents March. So this t stands for the month of the year. And the right-hand side, the left-hand side, it gives me the depth in water. It's the depth of the water. And does it say what it's in? It's the depth of the water in feet. Depths in feet of the water in the reservoir. Just like the last few problems, I'm going to sketch a graph. And in this case, The x-axis is going to represent the month of the year. It's going to start out at January, which is 1, February, which is 2, and it's going to go all the way to 12, which would be December. I don't have to graph all 12 months to answer the question. And the y's are going to be the depth, the depth of the reservoir in feet. So let me go ahead and sketch a graph. This is a table problem, so I'm going to change the number in the x column, put it in the middle of my table. That's going to stand for July. I'll do August and June. So this is going to be the month. June is 6, July is 7, August is 8. And the y's are going to be the depth in feet. And let me just get my table generated. So mode 7, 5, parentheses, alpha, x minus 7 squared plus 3. Start at June, which is 6, end at August, which is 8, step 1. And this is a really shallow reservoir. And in June it says a depth of 8 feet. In July it has a depth of 3 feet. And in August again it has a depth of 8 feet. So let me just graph these. Super easy to graph this one at least. So 2, 3, 4, 5, 6, which is June, 7, which is July, 8, which is August. In June, it's at 8 feet. In July, it's at 3 feet. And in August, it's back up. It started to rain again. So this is the graph of the parabola that maps the depth of the water. And I should be able to tell that this vertex is a minimum point, which means the y-coordinate of the vertex is smaller than any other y-coordinates. It's the lowest y-coordinate. 3 is the smallest y-coordinate that this graph will generate, and the y-coordinate is the depth. That means 3 feet is the absolute lowest the water will get. So the answer part A, how low did the water get? The smallest, the lowest it gets is 3 feet. And when did it? It did it at March 7, and 7 is July. Your problem 7 should work exactly the same way. And I think, I don't want to make this go into a second video. Let's see if we can quickly do 9 together and then call this an end. So 9 is similar to 7 and 8. It measures how much snow is at the base of a mountain. And I know in Flagstaff, by the time summer ends, Snowbowl is free of snow. But it gives me a function, and this function similarly uses a t that represents the month. 1 is January, 2 is February, 12 is December. It gives me this function, and in this function, the t represents the month, and this side represents the depth, or how much snow is at the base of the mountain, maybe the base of the ski run. And the question is, how low did it get and when did it get that mark? So I'm going to skip 10 and try to do this quickly. I'm going to make a table. The x's are going to be the month. The y's are going to be the depth of snow. And I do feet. The snow at the base of the mountain. It's a parentheses problem. I'm going to change the sign of the parentheses and go smaller and bigger. So September, October, November. I'm going to get a table by going mode 7 rather than doing it by hand. 4 parentheses alpha x minus 10 squared plus 15. Start at 9, end at 11, step 1. So it says in September, the base had 19 feet. That's pretty healthy. Apparently here the snow never goes away. In October, it has a base of 15 feet. It's definitely not Flagstaff. And in November, it's back up to 19 feet. May not be a very realistic problem, but I just wanted to make something that worked. So when I sketch my graph, I don't really have to sketch a graph, but on the x-axis, I need to get out through 11, and on the y-axis, I need to get up to 19. So I get the point 9 and 19, 10 and 15, 11 and 19. I get a graph that looks like this. The vertex is a minimum point, and this vertex, the 10 stands for October, the 15 stands for the 15 feet of snow at the base of the mountain, and the vertex is a minimum point, so it's the lowest the snow gets on that particular mountain during the year. So for part A, how low did the snow get that year? It got to 15 feet, and when did it get there? Sometime in October, which is the 10th month. That should be good enough. I usually don't ask these. I ask the first kind of problems on the test, not the second. My video's getting ready to hiccup, so I'm going to stop here. Just stop at number 9, do 1, 3, 5, 7, and 9, and that will be enough.